Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're here today. We are taking a really fascinating architectural tour of the universe's most basic building blocks. Whether you're staring up at a towering skyscraper, holding your phone, or just looking at your own reflection in the mirror, you are looking at matter. And today, we are going to completely decode the exact blueprints of that matter. So, what builds the universe? It's a huge question, right? And honestly, it's kind of mind-boggling when you realize that everything around us, and literally everything inside us, is made of the exact same tiny invisible building blocks. We just arrange them differently. Okay, let's dive into this. Here is our roadmap for today. We'll start with the building blocks of matter, decode those atomic blueprints, learn the rules of electron shells, explore the atom's quest for stability, and finally, we'll look at isotopes, the atomic twins. All right, Section 1, Building Blocks of Matter, the subatomic cast. To understand the whole building, we really got to meet the characters living inside every single atom. And wow, notice how insanely organized this tiny universe actually is? Right at the center, you've got that dense cluster, the nucleus. That holds our first two characters, the protons and the neutrons. Then, buzzing around the outside in those circular orbital paths, which we call shells, are the electrons. They are moving so incredibly fast, forming almost a sort of cloud around the nucleus. Now, if we look at the hard data for this cast of characters, it's pretty amazing how perfectly balanced they are. Protons pack a positive charge, neutrons, as the name suggests, are totally neutral, and electrons carry a negative charge. In a normal atom, the number of protons perfectly matches the number of electrons. This means the positive and negative charges just cancel each other out, making the whole atom electrically neutral. But take a closer look at that relative mass. Protons and neutrons both have a relative mass of 1, but look at the electron. 1 over 1840. I mean, seriously, it takes almost 2,000 electrons just to equal the weight of a single proton. The electron is so unbelievably light that its weight is considered virtually negligible in chemistry. It's basically the ghost of the atomic world. And because of this, practically all of an atom's mass is packed right into the center, tightly inside that tiny nucleus. Moving right along to Section 2, Decoding Atomic Blueprints, reading the periodic table. So we know what's inside the atom, right? But how do we actually identify specific elements? Like, how do we know if an atom is carbon or gold or oxygen? Well, it all boils down to two absolutely crucial numbers. First up, we have the atomic number, represented by the letter Z. This is simply the number of protons in the nucleus. And let me tell you, the atomic number is everything. It's the ultimate ID badge. If you change the number of protons, you literally change the element. Plus, since atoms are neutral, this number also secretly tells you the number of electrons. Then we have the mass number, represented by A. This is the total number of heavy particles in the nucleus. So that's your protons plus your neutrons. Now, honestly, it is incredibly easy to mix these two up when you're staring at the periodic table. So here is a highly practical pro tip. Think mass equals massive. Because the mass number includes both the protons and the neutrons, it is literally always going to be the bigger of the two numbers. The smaller number, that's your atomic number. And this brilliantly illustrates how the blueprint looks in real life. Take the standard atomic notation for carbon. You've got the C right there for the chemical symbol. Up top, we have the massive number, the mass number, which is 12. Down below, we have the smaller number, the atomic number, which is 6. So instantly, just by reading this blueprint, we know carbon has 6 protons and, because it's neutral, 6 electrons. But what about the neutrons? Finding the neutrons requires just a tiny bit of math. Don't worry, it's super easy. You just take the total mass of the nucleus and you subtract the protons. So mass number minus atomic number. Let's do a quick worked example together. Imagine an unknown element, let's call it X. It has an atomic number of 29 and a mass number of 63. How many neutrons does it have? Well, 63 minus 29 gives us 34 neutrons. Boom, simple, highly structural, and mathematically perfect. All right, part 3, the rules of electron shells, where electrons live. Okay, so we've got the heavy lifting in the nucleus sorted. Let's shift our focus outward. Those tiny, weightless electrons, they don't just buzz around randomly. No way. They have super strict zoning laws. Electrons live in specific energy levels called shells. And the golden rule here is that electrons will always fill the shell closest to the nucleus first, simply because it has the lowest energy. Only when that inner shell is completely full do they move to the next one further out. the very outermost shell that actually contains electrons. That's called the valence shell. Keep that word valence in your back pocket. It's going to become a real game changer in a minute. Because here's the thing. Each shell has a strict maximum capacity. The first shell, it's tiny. It can only hold 2 electrons. The second shell can hold 8. And for the elements we typically deal with, we use a simplified model where the third shell also holds 8. This is what gives us an electronic configuration. So if we go back to our old friend carbon, it has 6 electrons total. 2 go into that first shell, leaving exactly 4 for the second shell. So its electronic configuration is simply written out as 2, 4. Which brings us to section 4, the quest for stability, the drive for a full valence shell. You know, atoms aren't just passive little spheres. They actually have a primary drive, a real motivation. Every single atom is on this relentless, absolute quest to completely fill its valence shell, that outermost shell, with electrons. When an atom doesn't have a full outer shell, it's unstable, it's reactive. To achieve that perfect stability, atoms will actually give away or completely steal electrons from other atoms. And when they do this, they aren't neutral anymore. They lose or gain negative charges, transforming into charged particles that we call ions. If you lose a negative electron, you become a positively charged ion. If you gain a negative electron, you become a negatively charged ion. To see exactly how this drama plays out, let's look at magnesium. In its neutral state, it has 12 electrons, configured as 2, 8, 2. That outer shell has just 2 lonely electrons. Now, to get stable, it's way easier for magnesium to just throw those 2 outer electrons away rather than trying to somehow find 6 more. When it loses those 2 negative charges, it becomes an ion with a 2+ charge, dropping nicely down to a completely stable inner configuration of 2, 8. On the flip side, check out chlorine. It's configured as 2, 8, 7. It is desperately, frustratingly close to a full shell of 8. So it just steals 1 electron from somewhere else, gaining a 1- charge, and locking into a perfectly stable 2, 8, 8 configuration. And then we have the Zen masters of the periodic table, the noble gases, sitting coolly over in group 8. Elements like neon and argon, they are completely unreactive. And why is that? Well, because they are born with their valence shells perfectly, completely full. They have absolutely zero reason to gain, lose, or share electrons with anyone. They have already achieved the atomic dream. Finally, section 5, isotopes, the atomic twins. So we've established that the atomic blueprint is incredibly strict. But what happens when nature kind of tweaks it slightly, without actually changing the element itself? Well, you get isotopes. Isotopes are atoms of the same element that contain the exact same number of protons, so the atomic number stays exactly the same, but they have a different number of neutrons. Because the protons are identical, the chemical identity of the atom hasn't changed one bit. It acts exactly the same in chemical reactions. But because it has those extra neutrons, it's literally just a heavier twin. Same identity, different weight. To really ground this, let's look at a super famous one, carbon-14. Regular carbon, the stuff making up most of your body, has a mass of 12. That's 6 protons and 6 neutrons. But carbon-14 is an isotope. It still has 6 protons, so it's unmistakably carbon. It still has 6 electrons, but its overall mass is 14. If we do our math again, 14 minus 6, we see it has 8 neutrons instead of the usual 6. It simply packed 2 extra heavy subatomic particles right into its nucleus. As we wrap up this explainer, I want to leave you with a really provocative thought. Everything we've covered today, from the massive, dense nucleus to the almost weightless electrons desperately chasing stability in their shells, these are the absolute rules of the universe. Every reaction, every material, life itself, is all governed by atoms just trying to balance their protons and fill their outer shells. It's this vast, beautifully complex universe entirely constructed from remarkably simple structural rules. So what does this all mean for the future of how we manipulate matter? Thank you so much for joining me on this tour of the atomic blueprint. Until next time, keep questioning what builds your world.